Hey all, I'm Mike Lanzetta, and I'm a principal SDE or software engineer at Microsoft. And I am in a team called the Partner Catalyst team. And the goal of our team is to work with partners, startups, and labs on projects that are complicated enough or niche enough that Microsoft doesn't really have an out-of-the-box solution for them. And we try and take what we've learned from those projects and abstract them out into code that we can then open source and give back to the community. So we recently worked with a partner called Sierra Systems on a project for a customer of theirs called Pure Technologies that does leak detection in oil and water pipelines. And so I'm going to turn it over to Anthony Bulk from Sierra Systems right now to tell you a little bit more about the project.
All right, thanks, Mike. So I think we can all agree that having a leak in a pressurized pipeline is a problem that can affect anyone. Due to our aging infrastructure and just the sheer volume of pipelines, it's very hard to prevent leaks. However, imagine if there was a way to drastically reduce the amount of time required to detect a leak. This would allow us to respond faster to minimize the impact that these leaks have on everyone. And that is why Mike and I are very excited to talk to you today about a unique solution that solves this real-world problem that all of us can relate to. Nobody likes a leak. So as Mike mentioned, my name's Anthony Bulk, and I work for Sierra Systems, a top-tier IT services and management consulting firm. And our client, Pure Technologies, they develop unique applications for inspecting, monitoring, and managing critical infrastructure. And one of the products they have is called a Smart Ball. That's the device there on the right-hand side. Now, it's a device that does a free-flowing device that does leak inspections. And it's a great device because it can complete long leak detection surveys in a single deployment without disruption to regular pipeline service. So it does this by using a bunch of different sensors in it. And one of the sensors is a high-fidelity audio microphone. And this microphone, it records audio data as it travels down the pipe. And the microphone is sensitive enough to even pick up really minute pinhole-sized leaks. And what happens then is this audio data is analyzed to look for anomalies that resemble leaks. Now, the challenge is the amount of time required to analyze all of this data. And of course, when it comes to a leak, time is of the essence. The average analysis time is about 5 hours per kilometer, which is roughly 8 hours per mile. And it can involve 3 or more people. And as we all know, pipelines run for many miles, so you're looking at upwards of 50 hours per pipeline to analyze this data. And the analysis is done in 2 ways. Visually, by looking at it with audio spectrograms, and then also acoustically, with a good set of headphones and keen ears. So as you can imagine, this is a very manual approach that is very time-consuming. So due to the nature of the data and the techniques used by the client, we approach the problem as an image recognition issue. And with this approach in mind, we developed a highly innovative solution using Python and the Microsoft Cognitive Toolkit. So at a very high level, the process breaks down as follows. First, we take the raw acoustic data and we perform a fast Fourier transform. Now, this is a critical step because leaks have frequency characteristics that the neural network must learn to recognize. Then we go and enhance that data by adding some additional values that aid in generating pictures. Next, we need to balance our data by augmenting our leak data set. As you can imagine, leaks are not full of, or pipes are not full of leaks, thankfully. So we need to have a balanced data set for training and evaluation. And then in the end, we take those images and we trained and evaluated using several different architectures in parallel. And this allowed us to pick the right model to use in production. Plus, when using the toolkit, it's actually not too hard and kind of fun to assemble these models. And this approach has yielded excellent results. So a picture says 1,000 words. And when scaled and framed properly, the image of a leak becomes very obvious and very easy to use. So you can see there, the top 3 images are of sections of the pipe where there is a leak, and the bottom 3 are of sections of the pipe where there is no leak. So using this approach, we were able to develop a system that can process an entire pipe run in minutes as opposed to hours. So you can see by the infograph there on the right-hand side, we were able to process an entire pipe run in 20 minutes as opposed to 50 hours. This is and not only does it do it really quickly, but you can also scale this and process multiple pipes in parallel. So this is a huge reduction in the amount of time to analyze the data. It's a cut by 99.3%. So not only does this allow you to react faster, but you can also perform these inspections more frequently and have lower incurred costs. And the nice thing is that you still get the same level of accuracy when using a deep learning neural network. So it's essentially automation on steroids, and it's really a great example of using AI to solve a real-world problem. And now I'm going to hand it back over to Mike to walk us through some code.
Thanks. All right, it showed up. Yay. So I took the concepts of the code that we wrote for Sierra, or with Sierra, and I basically rewrote them in a way that they could run in a Jupyter notebook on a very limited amount of data and open source that out on GitHub. And I'll be providing that link later. So you can download it and use it yourself. It's under the MIT license, so take it and use it as you see fit. So as we mentioned earlier, we're using the cognitive toolkit for doing the detection. So the first thing we do here is not very interesting. We're just doing a bunch of imports. So we import a bunch of stuff from the cognitive toolkit. I'm also using Bokeh to do some plotting, so I can show you what the frequency looks like. And I'm using SciPy to read the waveform, and NumPy to do some basic processing. So if you actually listen to what this sounds like, this is what it sounds like when the leak starts, or when the ball starts down the pipe.
Hopefully you can hear it with the background noise. Yeah, there you go.
So there's not a lot going on. If you go to the center of the leak, you can really hear a lot more in the mid and high frequencies.
And so you can kind of hear the ball as it rolls past the center of the leak, that inflection point.
Yeah, so you can really kind of hear it Dopplering past. It's kind of interesting. So we take that same wave file that I just showed you, and we crack it using SciPy. So we use SciPy to read in the wave file, and that gives us 2 things. It gives us a sampling rate, and it gives us the data. And the raw data that we have, if you look there, is a bunch of just regular integer data, integer real data. So we're taking that data, and we convert it into the frequency domain using fast Fourier transforms. So if we look at this code below, I'm using the NumPy fast Fourier library to do the fast Fourier transform, and I'm using RFFT to transform the data. RFFT because it's real value data, it's not complex data. And I'm taking the absolute value because all we really care about in this instance is the magnitude. And then what I've done here is I've just done a few convenience methods to allow us to visualize the data. So you can basically pick a second, and it will plot out an offset, plot out a window basically from that second and allow you to take a look at it. So if you look at this below, this is at the beginning of the pipeline, and you just see there's low frequency noise, but not a lot going on. And as you move this across, you basically see, well, if it actually moves, you see the mid and high frequencies really start to spike once you get to the center of the leak.
And you might notice, too, how the wave fluctuates, and that's because as the ball travels down the pipe, the direction of the microphone's changing, of course.
So what we do is we take this insight of the frequency-converted data, and we're turning that into images. And the way that we do that is we basically are slicing it into chunks. And in this particular case, we're slicing it into 5-second chunks. So we take 5 seconds of that data, and we're converting it into images in a relatively easy way by basically taking those 5 seconds, we take the sampling rate, we figure out what segment of time that is, and we walk across that. And we take windows out of that, do fast Fourier transform to get the result in the frequency dimension, and we're taking that and turning it into an array of arrays. Once we have that array of arrays, we can convert it into actual images. In the real system, it converts it into grayscale images because the colors really provide no predictive value. They just really provide more demo value. So I'm importing Matplotlib's color map library and using a heat map color map to allow us to basically visualize that in a more interesting fashion. And so you can see here, that is basically the center of the leak. You can see a lot of noise. And to show you that this is actually running code, that is what not the center of the leak looks like. And you can see basically you just see low frequency noise and not a lot of else going on. So it's actually relatively obvious in this case because the leak is kind of a gusher. Once we have that data, we need to tell CNTK how to use it. And CNTK has an image deserializer that takes in these map file formats. So the map file format is basically just a text file that has, per line, the path to the image and the label for that image. And it's tab delimited. And in their case, they're very carefully labeling the leaks so that it's very appropriate. In our case, I'm super lazy. So I'm just saying the leak is this particular range of seconds that sounds about right. And I take that, I convert it into ones for leaks, zeros for non-leaks, and then I'm just using modulo 3 to basically say 2/3 of the data is in the test set, 1/3 of the data is in the 2/3 of the data is in the training set, 1/3 of the data is in the test set, and then I can actually start training. Now, since we have a very small amount of data here, training up a neural network from scratch is going to be basically impossible. And so in the real world, you actually want to do a lot of tuning and everything like that. In this case, we're going to rely on transfer learning to make that happen for us. So we're downloading a network called ResNet 18, which is a residual network. And it's kind of the baby brother of the one that Harry Shum talked about in his keynote, with the ResNet 152 network that we use in a lot of our stuff. This is the mini tiny baby version of that. And it's been trained on ImageNet, so it knows how to detect things like cats and dogs and boats. And what we're going to do is we're going to force it to detect leaks instead. And the way you do that is you rip off that last layer that says this is a cat, this is a dog, this is a boat, and you're relying on the feature layers inside that. And those have been trained to detect high-level features of images. They detect things like circles and crazy-ass lines and things like that. And we're using that as our feature set and basically adding in another judgment layer at the end that says this is a leak, this is a non-leak.
And actually, for our project with Pure, we built our own model because we wanted to keep it as lean and mean as possible, with the goal of maybe getting it out on a device, as close to the pipes as possible. So we didn't use transfer learning, but it's a great technique.
So once we have this model that we've defined, basically we know what we want to do. We need to define the mini batch mechanism for actually reading in that data, and we need to define the model creation method for creating that model. For creating the mini batches, there's something called the mini batch source, and that takes in the image deserializer I was talking about earlier. So you hand that image deserializer the map file, and it cracks it into two different streams. One for the features, which is basically the pixels of the image, and one for the labels, which is the 0 and 1 that we had in our mapping file. And so you notice there's randomization. You notice you can add transforms in here, so if the images are not the size you're expecting, you can convert them to the appropriate size. And that would also allow you to do things for training like randomization and clipping and things like that. And then creating the model, this is what I was talking about earlier. We load the model. That's the model we've downloaded. We find the last feature, the last hidden node of that model, and we basically clone everything up to that last hidden node and then add our own stuff on top of that. And then basically we need to tell it how to train the model. And this is actually, there's nothing exciting in this particular piece of code. It's just vanilla training code. And I actually stole this from the transfer learning tutorial, which I felt obliged to do because I helped write that. So I thought I had a right to do it. So if you look at what it's doing here, it's using the mini batch source that I defined earlier. It's creating the model. It's using cross entropy with softmax. It's defining the classification error. And it's basically picking out the learning rate and the momentum, which if you don't know deep learning, none of that made any sense to you. But feel free to talk to me afterward, and I can try and explain some of it. But the upshot is that you can steal this code and use it and do your own deep learning with it. So that makes it easy to kind of get up and running.
Yeah, as Mike mentioned, the cognitive toolkit is full of great examples and tutorials and recipes to help developers and data scientists get going really quickly. It allowed us to kind of play with several different popular architectures and ultimately develop the best model for our situation.
And then the evaluation code, once again, I stole this. So what I'm doing here is just cracking the image, turning it into features, and then doing evaluation in softmax to actually get the probability of whether it's a leak or a non-leak. And then I evaluate a set of images all at once, and that gives me the total results so that I can basically tell you what the actual final results are. So at that point, I've defined all the methods, and we're ready for execution, and we're ready for training and evaluation, basically. For training, you define a set of hyperparameters that you're going to use to train your model. And this is where you would wind up doing a lot of work on your side to do tuning and making sure this is the right thing, and hopefully using up a lot of Azure GPU time. In our case, we're just training for 20 epochs because we don't have a lot of data here, and we're relying on transfer learning. And we're using kind of standard sets for our learning rate and momentum. We train the model. I'm not going to train it in real time because that's super boring to watch. But you can see here, it gets trained, it gets saved out to the file system so you can load it up later and do evaluation on it. And then we evaluate the results. In this case, we get 9 out of 12 right, which is not bad considering how crappy our data was. We had very little data. And then you can plot that in a confusion matrix and see what it got wrong. So you can take a look. It did mostly right. It got all of the leaks correctly. It predicted leaks. So it got 3 basically wrong out of 12. So not too bad. In the production system, in their system, they have quite a bit more data and have done a lot more experimentation than I did here.
Yeah, and so we're at the point now where we're trying to find out kind of the best way to slowly improve and evolve the model over time and to manage it. And we're also discussing the addition of a more sophisticated supermodel to help further classify the images. I mean, I think the ultimate goal would be to have one lean and mean model on a device as close to the pipes as possible, so you could immediately let the pipe owner know, yeah, you have a problem. And then the secondary model would further classify those problems and say, yeah, that problem is a crack or a pinhole or a large hole. So having the two models kind of work together would provide the best overall solution.
So the call to action here, our example code is out on GitHub. I put a tiny URL because the GitHub URL is quite long. Our code story is published on our blog. You can go take a look at it. That also has a tiny URL for your benefit. The cognitive toolkit tutorials, there are a few that would be useful for you. The 2 main ones are image recognition, and that will tell you how to build a convolutional neural net using CNTK. The other one is transfer learning. That will tell you how to avoid having to build your own and benefit off of stealing someone else's work. And then this session and all the build sessions are taped and put up on Channel 9, so you should be able to revisit it later. And there's additional training in the Microsoft Virtual Academy. And please complete an evaluation form for all the sessions that you see here today at Build. It's very useful. And then I wanted to open it to a very brief Q&A. I'd like to show a video as well from the partner to tell you a little bit more about the problem. But I will be off the stage and answering questions afterwards. So if you have any deep questions, I can definitely address them after the session. You have anything brief? Sorry.
Yeah.
So the question was, what was the size of the image set for training the neural net for the production system? Do you want to handle that?
Yeah, so essentially, we got to a point where the client has like over 700 leaks, and we tried to progress in a really methodical method. And so in our first sprint, we worked with 10 leaks, generated a bunch of pictures off of that. Second sprint, we added to that, more and more and more. And eventually, by the 4th sprint, we had, I think, 2,000 or 3,000 images. And at that point, we now had a model that gave us, high enough accuracy that we could, look towards putting it into production. And so that was a really good technique to kind of, tackle the problem, essentially.
Well, thank you guys so much. I'd love to show you a brief video from the partner. And then, like I said, I'll be over here answering questions.
Pure Technologies is a world leader to provide condition assessment information for oil and gas and wastewater pipeline owners and operators. SmartBall is one of our patented technologies that we use for leak detection in water and wastewater pipelines. The goal of this project was to partner with Sierra and Microsoft to use some new machine learning techniques to automate the data analysis process a little bit quicker.
Our advanced predictive data analytics-based model typically processes the audio output from a single 10-kilometer pipeline into a set of 1,100 images and analyzes them in just a few minutes.
This has allowed our data analysts to focus on some other aspects of our inspection technologies and business.
This project utilized the Microsoft suite of technologies and cognitive tools in order to take very complex and very substantial amounts of data through an analytic process in order to create models to streamline efficiencies and reduce the amount of manpower hours that it takes to provide the results. At the end of the day, 50 hours per 10 kilometers of pipe could be done in a relatively short period of time, and the end result was around 20 minutes per 50-hour equivalent to provide exceptional efficiencies with a high accuracy return result.
So the Microsoft Cognitive Toolkit has enabled Pure Technologies to increase their pipeline processing from 1.5 kilometers today to over 225 kilometers a day. That's got massive business impact.
Thank you very much.
Thank you.